Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. So the topic is knowledge-based agents. This is chapter 7 in the book. This is an outline, so let us begin. So knowledge-based agents, we denote them as KBAs or just KB agents. They use reasoning over an internal representation of knowledge to infer new facts about the environment. So the keywords here are reasoning and the inference of new facts. So far, problem-solving agents that we've seen are limited in their reasoning. They cannot reason and infer new facts about the environment. They're limited when dealing with partial observable environments. So far in this course, we've had fully observable environments. And so the algorithms we discussed, you would need to adapt them. For those interested, they can check out these chapters in the textbook. However, even with these techniques that are in the textbook, you would just have too many state spaces to cover. Whereas knowledge-based agents, what we're going to see in this topic is that they will apply logical inference rules, which are, some way of reasoning. They use a set of logical statements, so we'll use logical languages, and we will use logical inference rules. Here's a sketch of where the knowledge base in a knowledge-based agent comes in. If you remember our rough sketch of the environment and the agent interacting, where you have an environment, you have precepts that the agents can receive in terms of through the use of sensors, and then the agent can have code running where he maintains some memory. He has a state for the current state of the environment. Now, where the knowledge base comes in is that you have a component, which is your knowledge base, and an inference engine as well. Your knowledge base is kind of like a database. This database contains facts or evidence that you have about the environment. And what you would like to do is that as you get some initial facts about the environment, so based off of some assumptions on the environment, your knowledge base will contain these facts. Then as you operate in the environment, the agent will receive sensors, and you would like to update the state, of course, but you would also like to update new facts and receive new facts from the environment. So facts received from the environment, you can then add them to your knowledge base. And then furthermore, what you can do is that the agent can use the facts in the knowledge base and the inference engine in order to, ask the knowledge base questions like, is some situation in my environment true or not? Has the goal been achieved or not? This is especially useful if your goal is, it changes, and you would like to check using logic whether the goal has been achieved if the goal, the goalpost changes. So the way it works is that you have sensors. There's some code that processes the sensor data and then updates your knowledge base with new facts as well as the state. And you also have some code which is your AI decision making. This code uses the current state as well as querying the knowledge base, asking it questions and receiving new information or inferred information back. Like one question you could ask it is there a pit in this location? Especially if the agent doesn't know the presence of pits. But you can ask your knowledge base, is there a pit in this location? And the knowledge base can reply, yes, there is a pit there, or I don't know if there's a pit there. And it uses logic to infer this information. And your code can then use this inferred new facts in order to reason about what is the best action to take. So these are useful techniques for certain types of environment, and we'll actually show some use case for this at the end of this topic, inshallah, when we do activities in class. So we'll work with this toy problem. This is called the Wampus world. Some of you have seen this before, but in the Wampus world, it is just an n by n grid environment, right? And in this grid, you can have a couple of things. So you have your agent. The agent always starts in 1-1. Of course, you can make him start in different places. The agent can move forward. He can turn left. He can turn right. He can shoot. He only has one arrow. He can grab the gold, and he can climb, which is only applicable in the starting location. So that means he has an orientation, and you can, rotate around. In terms of what is available in the environment, there is a wampus, which is an enemy. If the agent moves into the wampus, he dies. The wampus emits a stench in his adjacent locations. There's gold. The gold emits a glitter. There are pits. If the agent moves into pits, he dies. But the pits themselves, they emit a breeze in their adjacent locations. The agent, when he starts the game, he doesn't know the location of the pits or how many there are, and he doesn't know the location of the wampus either. But the idea is that he can, perceive at every timestamp within his current location these following senses. He can sense the stench, the breeze, the glitter, the bump. Bump occurs when an agent moves into a wall, and a scream. This occurs if he kills the wampus. So the perception is a vector of these booleans, right? They'll be 0 or 1 depending on whether or not he sensed this in his current location, right? And the goal is for him to navigate this environment, get the gold, and then move back, right? So there are a lot of unknowns here, partial observability, and so how can we deal with this using a knowledge-based agent? Of course, there's always assumptions. This is some assumptions related to this particular environment. The agent knows the starting location. Agent doesn't know where the pits are, doesn't know where the wampus is, doesn't know, but he does know the rules of the environment. He knows, for example, that if there's a breeze here, like he senses a breeze here, he knows that there might be a pit here, a pit here, a pit here, or a pit here. Uh, Yeah, you can always make random instantiations of this problem by making a random grid and then a random starting location, random location for the gold, and random location for the other entities. So how can I use logic and inference in order to reason about this environment? So I'm just going to show in English how we can do this. So let's say this is the current state of our environment. The agent starts in 1-1. And the agent knows it is in 1-1, and he knows that 1-1 is safe. When he's in 1-1, he receives the following first precepts: false, 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 right? Because he receives false, 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 which is for stench, breeze, glitter, bump, and scream, he doesn't sense any stench, he doesn't sense any breeze, he doesn't sense any glitter. That tells him that there's these locations 1-2 and 2-1 is clear. They're good and safe, right? So we denote this as okay, as safe grids, right? This is important. This is called inference. We used our logical inference, our brains, to reason about these mechanics of the environment, as well as this sensor reading. We reasoned that these grid locations should be okay. So we want to make forward progress. We could tell our agent at this point, right, make forward progress towards a location that is clear, right? So let's say he moves to the cell 2-1. So the agent moves here, okay? Now the agent is here. Let's say he receives a breeze. He perceives it. Because he perceives the breeze, using, again, inference and reasoning, we could infer that, there's a pit here or there's a pit here. I don't know which of these two the pit is exactly in, but this is the possibility, right? A cautious agent, right? Because he doesn't want to die, and we don't want to be risky. We still have this location we can explore, right? So we can try to go back and try this location. So now we're here. He perceives a stench. Because he perceived the stench, right? He can infer the following. Remember, he had beforehand is there could be a pit here. Okay. When he moved to this location and he perceived a stench and he did not perceive a breeze, that tells him that for sure the pit has to be here. This is using reasoning, and the pit cannot be here. Otherwise, if the pit was here, he would have sensed the breeze here as well. And it must be the case that, the wampus is here, because if the wampus was here, he would have sensed a stench here, right? So all of this reasoning that we did to infer that there's a pit here, there's a wampus here, and this is okay, is using reasoning and logic, right? And the reason we were able to do this is what you notice is that as we're moving along, we're keeping all this information, right? Okay, there's maybe a pit here, there may be a wampus here, in our knowledge base, right? In our database of knowledge, right? And again, now he can, using what he can tell, he said, I want to make forward progress. I'm definitely not going to go here or here because I will die, so I'll move here, right? After some time, he moves around, and let's say this is the current situation of the environment. When he moves here, he perceives a glitter, right? So he will the, grab the item, and then because of his knowledge base, he already has a safe, path back to the starting location. So what we just seen in this example is that our knowledge base represents knowledge of the environments, right? These are a set of facts that we know to be true. Like there's no pit there, there's a breeze here, there's a stench here. We used rules, mainly our logical rules that we have in our brains, and using the facts that are in our KB and the rules, we were able to infer new facts, right? We were able to infer that there has to be a pit in this location based off of previous facts. This is called inference, right? And inference are guaranteed to be correct if your evidence in your knowledge base is correct, your rules that you're following make logical sense and they are correct, and the inference procedure that you use is correct, right? And we used English language to do all of this so far. So now let us formalize it using one type of formal logic language, which you've already taken in previous classes, called propositional logic. So what is logic? Logic is formal language to represent knowledge such that conclusions can be drawn. A knowledge base is a set of sentences. That is what a knowledge base is. So when we have a knowledge base, it is just a set of sentence 1, sentence 2, all the way up to sentence K. And when you infer new facts, use these sentences to add more sentences to your knowledge base. Syntax in a logical language, it defines the legal sentences in a language grammar. So for example, if I was using the arithmetic language, then I do know that x plus 2 greater than or equal to y is one sentence. This is well formed, right? Because this is something we agreed upon in arithmetic language. However, if I showed someone this, this is not a common format, and so this is not a well-formed sentence. So this is related to syntax. Whereas semantics is related to the meaning of the sentence that you're looking at. So for our case, it defines the truth of each sentence with respect to each possible world. So when we say that x plus 2 equals y, this sentence is true in a world where we set x equals 7 and y equals 9. X plus 2 equals y is false in a world where we set x equals 7 and y equals 1. The reason it's false is because, we've defined meaning to what plus is and what equality is, right? More examples you can look at from the language of arithmetic just to make this concrete. But the idea is that every formal language has sentences, and sentences have a syntax that is defined by the language, as well as semantics in terms of what's true and what's false. Another aspect of logical languages is something called models and the concept of entailment. Right? If you don't get this now in this slide, we will give more and more examples in the coming slides until the concept of models and entailment becomes clear, inshallah. So in logic, we have models. And what a model is, it is a configuration of the variables involved that establishes the truth or falsity of a sentence. For example, if we looked at this arithmetic sentence, x plus y equals 4, which configurations of the variables x and y does this make it to be true? Of course, we mean in the semantics of what we mean by plus and equality, right? In terms of arithmetic. So this is true for models for the following model. If we set x equals 2 and y equals 2, this makes this sentence true, right? Because 2 plus 2 equals 4. Another model for which it is true if we set x equals minus 1 and y equals 5. And so there are many other possible models, but a model, right, is a configuration. And so we can say that it is true in all models that set x and y as numbers that satisfy the semantics here, and false in other models. If a sentence alpha is true in a model M, then we say that M satisfies alpha, or M is a model of alpha. Okay? So for example, the model x equals 2 and y equals 2 satisfies the sentence x plus y equals 4. M of alpha is the set of all models of alpha. That is, it is the set of all models in which alpha is true. So if we have a sentence in any logical language, and we denote the sentence as alpha, when we say m of alpha, we are looking at all possible models, meaning all possible configurations of the variables involved in the sentence that make the sentence true, right? So I hope it is very clear. M of alpha is the set, right? It is the set of all possible configurations of the variables involved in alpha that make it true. It is the set of all models. And why are we talking about models? Why are we talking about, these concepts of ML alpha? Well, for one simple reason, to make progress towards logical reasoning, meaning the engine that we use to make and infer new facts. We introduced this concept called entailment. Entailment is the cornerstone of inference. Entailment, this is the formal definition. Entailment denotes that a sentence follows logically from another sentence. We write this as alpha entails beta. We say it as alpha entails beta. When we ask, does alpha entail beta? This is a question and not a logical statement. A logical statement is either true or false. So I want to make it very clear. When we say alpha entails beta, this is not a sentence that evaluates to true or false. Instead, this is just a question that is either whose answer is either yes or no. Okay. So when we ask, does alpha entail beta? We are asking, if we know that alpha is true, does it mean that beta is also true? Formally, alpha entails beta if and only if in every model in which alpha is true, beta is also true. That is, the answer to this question is yes, if and only if the subset of models or the set of models in which alpha is true is a subset of the models in which beta is true. In other words, you can think of the space of all variables as this very large set. This is the space of all variables involved in your environment. Beta is one sentence and it contains some variables involved in your environment. Alpha is another sentence and it contains some variables involved in your environment. For your sentence alpha, M of alpha is the set of all possible configuration of your variables that make alpha true. M of beta is the set of all possible configuration of your variables that make beta true. And so the only time we can say yes to alpha entails beta. So given that alpha is true, when is beta true? Alpha is true if the set of all models in which alpha is true is a subset of all the models in which beta is true, right? This is the formal definition, okay? And we'll look at situations when this does not hold, meaning when the answer to alpha entails beta is no, right? We'll look at when does this happen. So again, if you don't understand what's happening so far, we're going to give examples again and again. So entailment with the knowledge base. So how do we establish entailment? Just to show you how we can use entailment to infer new facts about the environment. Recall the Wampus World example. Consider this particular situation on the right. What do we have so far in our knowledge base? Our knowledge base contains the following facts. We know that 2-1 has the agent and there's a breeze and it is safe. So this is this situation here. We know that agent knows that if he detects the breeze, then there's a pit in an adjacent square. So these are related to mechanics. We know that 1-1 is safe. We know that 1-2 is safe. And we know that 2-2 or 3-1 contains a pit. Okay. So this is given for this current environment status. This is our facts in our knowledge base. Consider the following query. So let us ask the knowledge base the following question. Does the location 1-2 or 2-2 or 3-1 contain a pit, right? That is the question we would like to ask, right? How can we use entailment to answer this sentence, right? This is a sentence. Ignoring the KB facts, the question is, how many possible models configurations are there for pits in these locations? So just looking at pit status, right? If we look at these locations, 1-2, 2-2, and 3-1, there are two choices per location. It can either have a pit or no pit. That means for these three locations, there are 2 to the power of 3, which are 8 models. Based on the knowledge base, right? How many possible models are there for pits in these three locations? So I wanted to make it clear. If we ignore the knowledge base facts, the number of possible configurations for these three locations is 8 possible configurations. However, because we have information and facts in our knowledge base, it actually restricts the number of models from 8 to a lower number. Why? Because we already know from our knowledge base that 1, 2 doesn't contain a pit, right? So that means we are left with, two unknowns, the location for 2, 2, and 3, 1. So based on our knowledge base, how many possible configurations? From the fact number 4, which is this, the agent knows there's no pit in 1, 2. From fact 5, which is this, pit is in both squares or one of them, so there are 3 possible models. So from fact 5, we know that there's a pit in 2, 2 or 3, 1. That tells us that there's either a pit here and no pit here. That's one possible configuration, right? Or there is no pit here and there's a pit here. That's another possible configuration. Or, there's a pit in both locations, here and here. That's another possible configuration, right? So from fact 5, pit is in both squares on one of them. So these are 3 possible models. Thus, for a given query, which is this query, KB is true in just 3 models out of the 8 models. So these are only the 3 possible configurations. So from 4, agent knows there's no pit. From 5, agent knows hada. These are the 8 possible configurations for the 3 locations, right? In terms of pit or no pit, you can see them, the 8 possible configurations. Based off our knowledge base, these are the possible configurations based off of our knowledge base. So the idea is that the facts in your knowledge base will actually restrict the number of models that are possible in your current situations, right? So if we're assuming that all the facts in the knowledge base is true, these are the only 3 possible models that you see here, okay? Now, we already, like I said, these are the possible configuration or models in which the knowledge base is true. Let us look at how inference can be used or entailment can be used to infer new facts. Consider the 2 following queries. Alpha 1, there is no pit in 1, 2. Alpha 1, if you look at this query, there is no pit in 1, 2. This represents these 4 possible models, right? We're looking at location 1, 2. Location 1, 2 is this location here, right? We mean this location here, right? So in this location, there is no pit in 1, 2. It is these 4 models that you see here. These other 4 models, they do contain a pit. The other query is alpha 2. Alpha 2 says there is no pit in 2, 2. This corresponds to these set of 4 models. We notice from the figures that the models in which KB is true, alpha 1 is also true, right? If you look at this, these set of 3 models in which the KB is true, these 3 models are also part of the set of models in which alpha 1 is true, right? Recall the entailment definition. KB entails alpha if and only if. In every model in which the KB is true, alpha 1 is also true. And if you look at this, these 3 models in which the KB is true, it is also the case that they are true in alpha 1. What this tells you is that, does the KB entail alpha 1? The answer is yes. That is, we can infer that because the KB is true, it follows that alpha 1 is also true, right? Because this condition holds, right? So what this means is that we have a KB. We ask the question, does the KB entail alpha 1? Because this condition holds, we say yes. What you can do is you can take alpha 1 and then add it to your KB facts because it is a true sentence. So this is called inference. We use entailment and we base it off of this rule set here. Okay, what about alpha 2? Does the knowledge base entail alpha 2? The answer is no, right? The answer is no. KB does not entail alpha 2. Why? Because if you look at the set of models in which the KB is true, which are these 3 models here, It is not a subset of the set of models in which alpha 2 is true. You see that alpha 2 does not contain these two models here. And so we cannot say that alpha 2 is a true statement. We can't say this, right? Can we say that alpha 2 is false in this case? No. We also cannot say that alpha 2 is false. The reason is because in reality, because of the KB, assuming that the KB facts are true, in reality, right? Meaning if the real situation for your environment, it could be this situation, it could be this situation, or it could be this situation. All right. But you don't know which one so far. Maybe if you explore the environment more and you get more facts, you would be able to know which of these three is the exact situation. As you gather more facts, what happens is that the set of possible models for your knowledge base shrinks. So your M of KB becomes smaller and smaller, right? Until you know exactly what is the current situation, right? You will only have one model in your M of KB here, right? But so far we say that it could be one of these three models, this one, or this one. So does KB entail alpha 2? No, but this doesn't mean that alpha 2 is false, because remember, alpha 2 contains these four models, right? It could be the situation that as you gather more information, you find out that the KB just involves this model here. And so now, once you've gathered enough information, this situation has hold. And so alpha 2 now is a true statement that you can add to your KB, right? So I want to emphasize the question KB entails, a sentence is not, it's a yes or no question. If the answer is yes, then that means that alpha 2 is true. But if the answer is no, that doesn't mean that alpha 2 is false. It just means that we don't know as of yet. It could be true, it could be false, but we cannot tell, right? So does not say that alpha 2 is false. All this says is that the KB cannot infer whether or not alpha 2, whether alpha is true. Okay. So this example shows how we can use entailment to derive conclusions, that is to establish the truth of a query. This process is called logical inference. We use entailment, right, to infer this. This specific algorithm that we've just shown, where we look at models and possible configurations, this is called model checking, because it enumerates all possible models. So as a summary, what I want to say in terms of visualization is, does alpha entail beta? We follow this rule set. You can have three possible situations, right? The answer to it is yes, because your set of models in which the KB is true, M of beta is also true. The answer could be no. Why? Because you may have, your M of alpha being not being a subset of your M of beta. Some model in which alpha is true, beta is false. This doesn't mean that alpha is a false statement. All it means is that we don't know so far. And you could have complete intersection, right? And in this situation, you can tell that, beta is a false statement if you actually enumerated all possible configuration. So what we're interested in is the following. Does alpha entail beta? The answer is yes. If it is yes, then you can tell that beta is a true statement. If it is no, you can just say that we don't know as of yet. So let us talk about inference algorithms. Algorithms for establishing entailment are called inference algorithms. So far what we've seen is we understood the concept of KB entail alpha, which is, the process of entailment. However, what we want to do is we want to write algorithms that will do this process for us. So what we mean is the algorithm will take in the KB and the alpha, and then it will answer this question, yes or no. So in terms of this, we would say that an inference algorithm I that derives alpha from the knowledge base, we denote this process as KB derives alpha by the algorithm I. We want our algorithms to have two desirable properties, soundness and completeness. So what we mean by this is that an inference algorithm I is sound if it derives only entails sentences. Another way to say this is what we see here. An algorithm I is sound if whenever the algorithm I, uses the knowledge base to derive alpha, it is also true that this sentence is a yes. Sorry, this statement or this question is a yes, right? So if the algorithm I derives alpha from the KB, it is also true that KB entails alpha. This algorithm is said to be sound, right? So what we'd like is a sound algorithm because we don't want it to derive sentences that are not entailed. So if you have an algorithm that is unsound, right, what may happen is that, let's say that for a particular alpha and a knowledge base, the answer to KB entails alpha should be no, right? If your algorithm is unsound, you may give it the KB and you may give it the alpha and it may return yes, even though that it shouldn't, right? So when we say that an algorithm is sound, it means that the answers or the or the alphas that it is able to derive, it also is that this the answer to the entailment question is yes. So this is a sound algorithm. We don't want unsound algorithms. An inference algorithm is said to be complete if it can derive any sentence that it entails. So in other words, I is complete if whenever KB entails alpha, means the answer to this question is yes, it is also true that the algorithm I is able to derive this alpha sentence, right? And so an inference algorithm can be sound but not complete, right? You can have an inference algorithm that is sound, meaning that if it derives a sentence, it is also true that that sentence is truly entailed. Incomplete, how would it be incomplete? It means that there might be some entailed sentences, some alphas that is entailed by the knowledge base for which it cannot derive it, right? That's what it means to be sound but not complete. An inference algorithm can be complete but not sound. What this means is that for every single entailed sentence, it is able to derive it, but it also might derive some sentences that should not be entailed, right? And so these are the two properties. We want to talk about a couple of inference algorithms right now that we can use to, perform this entailment procedure, and we will look at their soundness and completeness. So we want to cover. So what we want to cover. This is an overview. We want to cover inference algorithms that can be used to infer new facts from a knowledge base. This requires us to use a logical language and then appropriate inference algorithms for that languages. There are two logical languages that are popular. There's propositional logic and first order logic, and there are other logical languages for this. We will focus mainly on propositional logic. And inference algorithms can be divided roughly into two kinds. You have a truth table enumeration type of algorithms. This is called model check-in, which you've just seen an overview of. This has exponential time complexity. And you have theorem proving algorithms. These are algorithms that apply rules of inference directly to the sentences in your KB in order to construct a proof or infer. Construct a proof means to infer the desired query or sentence. And there are a couple of approaches to theorem proving. You can go direct proof. This also has a worst case exponential time. You can do by contradiction. There is a known algorithm called a resolution-based theorem prover that we'll discuss. Also, worst case is exponential. You can sometimes make this fast in practice using modern stat solver, but this is not guaranteed. And you can have forward and backward chaining type algorithms. These are restricted to knowledge bases with specific format called horn clauses, which we'll discuss. The good thing about this is that they are linear time algorithms. These are used by logical programming language systems like Prolog. So we'll discuss all these types, inshallah. So let's start. What we'll do is we'll discuss all of this using propositional logic. So just as a reminder, propositional logic, this is the syntax of it. In propositional logic, we can use it to represent sentences. A proposition is a statement or a sentence that is either true or false. The syntax of PL defines the allowable grammar of the sentences. You can have atomic sentences. These are single propositional symbols. Another name for this is literals, right? So we just represent them as, a single like P, Q, R. This is the typical notation to represent them as uppercase letters. There are special symbols for true. This is the always true proposition, and false. And if you remember, the complex sentences can be formed using the logical operators. So this is the negation, this is the and, the or, the implication, and the biconditional. And this is the grammar for propositional logic, right? So I'm sure most of you know all of this from previous classes, right? And in terms of semantics, the semantics define the truth or falsity of a sentence. In propositional logic, when we talk about models, meaning configuration, what we mean is that a model is a true or false configuration of the symbols that make the sentence true. So for example, if we have symbols P, Q, R, then one possible model is M1 equals, where we set P1 equals true, or P equals true, Q equals false, and R equals true. That is one possible model for these three symbols. An example, and in terms of the possible models for the two propositional symbols P and Q, you can have this, and these are some examples of the regular sentences, right, or the simplest sentences you can form, right, and these are their semantic truth values. Here's some more examples, right, in terms of the semantics. Okay, let's now talk about inference algorithms using propositional logic. We use inference algorithms, like I said, to establish KB entails alpha. And as I mentioned, algorithms are divided into two kinds: truth table enumeration. It'll be exponential in the number of propositions, so O to the power of 2 to the power of n. This is in propositional logic, and we'll see why this is the case. And we'll also look at theorem proving, where we look at a direct proof and a proof by contradiction. So let's look at model checking using an example. Suppose you're giving a knowledge base. Your knowledge base contains two sentences, A or C, and another sentence, B or not C. You're given a query alpha, which says alpha or B. Where it says A or B. Does the KB entail alpha? We can answer this using truth table enumeration. So this is the truth table. The truth table contains a column for every possible symbol in your knowledge base. So if you look at our knowledge base and the query, there are three symbols, A, B, and C. And it also contains column for the sentences in your knowledge base. So this is sentence 1, this is sentence 2 in my knowledge base. And it contains a column for your knowledge base. But in essence, the number of rows in your knowledge base is the number of possible models for your variables, right? So in essence, when we look at this, question, there are only three possible variables, and so we should expect 2 to the power of 3, which is 8 possible models or rows. That's why you see 8 rows here, right? And the remainder columns are just the sentences and the evaluation of the remainder, right? And we evaluate this to false or true based off of the semantics of propositional logic. So if you look at this table, it looks fine, right? A or C is false because you can see that A is false and B and C is also false. It's true here because A is false and C is true, and so on, right? In terms of the column for the KB, this is true if all the sentences in your knowledge base is true. So you can see this is true because both of these sentences are true. True here because both these are true, and so on. KB is true when all of its sentences are true. Okay. This is our alpha. We just added it as a column. All right. And when we added it as a column, I want to answer the question, does KB entail alpha? If you remember our condition that we use, KB entails alpha if all models in which the KB is true, alpha must also be true. In other words, if all the rows in which the KB is true, alpha is also true. So if we look at the rows in which the KB is true, this is this row, this row, this row, and this row. All the rows in which the KB is true, you can see that alpha is also true. So the answer to this question is yes. If we had, for example, this was false, we just need one, then the answer would be no. All right. So Based off of what we have here, the answer is yes. And so, yes, alpha is true. And so we can add alpha to our knowledge base here. Right? We add a new fact to our knowledge base. Right? So this process of enumerating the possible models, and checking your knowledge base truth and falsity and your alpha truth and falsity and checking, this condition, this is called model checking or truth table enumeration. Can we do this with, a more complex example? Yes. If you look at the Wampus world, let us apply model checking in propositional logic. Let us use the following symbols. Pij denotes if there's a pit in ij, and bij denotes if there's a breeze in ij. In the situation shown in the figure, which is this situation, we just consider the relevant propositional symbols because I don't want to make, this knowledge base too long. So if we look at the situation here, and we just want to look at these, these propositional symbols here, right? These are the relevant propositional symbols related to these locations. The knowledge base, based off of this situation, has the following facts. It will just denote as, this is just noting the sentence. We're labeling the sentences R1, R2, all the way up to R5. So for R1, there is no pit in 1-1, right? And you can see here, there's no pit in 1-1. For R2, it says that if a square is breezy, if and only if there's an adjacent pit, this is a mechanic. And another one, we need to add it again. We need to add this mechanic for all possible grid locations. So because we're just looking at these grid locations here, I'm going to add it for only B11 and B21. However, in your knowledge base, this mechanic here, you would like to add for all grid locations. So you need to add it for B33, B43, B44, all these 4x4 grid locations. Okay, what about R4? There is no breeze in 1-1. This is from the precept, and there is a breeze in B21. So this is our knowledge base. How many possible models configurations for these number of symbols? It is 2 to the power of 7, which is 128, because we have 7 symbols. Does the KB, here's a question we want to ask it, does the KB entail that there is no pit in 1-2? Well, we can answer this by enumerating all possible models. So we'll have a table where we have these columns here, right? And we expect to see 128 rows. And then we need to take, and evaluate these sentences. We then find, where the KB is true. And we also have to have a column for not P12. And we need to see that the rows in which the KB is true, it is also the case that it is true in the alpha, right? So if you look at a knowledge base, these are the rows in which the KB is true. And if you look at P12, our statement alpha is, not P12. You can see that this will be true, this will be true, so this will be true. So yes, the rows in which the KB is true, our alpha is also true. And so we can say that, does the KB, the answer to this question here, does the KB entail not P12? The answer is yes, right? So this is how you would do truth table enumeration. You can write a simple depth first search algorithm for it, right? Here it is. We won't go into too much detail of it, but what this does is that, it starts with a binary, it's going to be a binary tree where at each step, it will select a variable to assign true or false, right? So in the beginning, your assignments are empty, but then it selects a variable and then it assigns it true. So maybe it assigns P true, and then it keeps going down the tree until it assigns all the variables true or false, and then it also checks the locations in which the KB is true. Is alpha also true and not, right? So you can do it the table way, or you can do it the depth first search way. Both ways are possible. Model checking, which is this truth table enumeration, is sound and complete inference algorithm. So this is good properties to have. What's the catch do we have with this? Well, if you have n symbols, that means you need to check 2 to the power of n possible models. So time complexity is 2 to the power of n. Space complexity with this implementation is on, right? So really, time complexity is a big issue. So we need more efficient inference algorithms than using model checking. Model checking is not very efficient. Is this possible? Well, unfortunately, no. Propositional entailment, meaning if you want to answer this question in the general case and you're going to use propositional logic for this, it is co-MP complete. No need to go into the detail what co-MP complete is, but just simply it is probably no easier than MP complete. So it's a hard problem to solve. Every known inference algorithm, so all the known algorithms that we have so far for entailment in propositional logic has a worst case complexity that is exponential in the size of the input, right? So we really can't do better than exponential time algorithms for entailment in propositional logic for a general knowledge base. What we'll see later, inshallah, on this topic is that for specific type of knowledge base that have a specific format, we can get away with getting linear time, right? But for a general type of knowledge base with general formatting, it is exponential. So we looked at the model checking way. Let's look at theorem proving inference algorithms. In theorem proving inference algorithms, we will apply inference rules directly to the sentences in the knowledge base in order for us to construct a proof of the desired sentence. In practice, using a direct theorem prover can be more efficient than model checking. Okay, the reason is because the number of models, meaning the number of rows or the number of possible configurations you need to check, is going to be exponential. But the proof may be short in practice, meaning you just need to look at a couple of direct rules to prove this. So, however, the worst case remains exponential in propositional logic. The good thing about this is that using inference rules, this is sound inference procedure, so that's a good thing. So we can use these inference rules as operators in a standard search algorithm. So we'll show and discuss what we mean by this. Some important concepts we want to discuss first is logical equivalence, validity, deduction theorem, and satisfiability. So let's talk about all of this. Some useful rules for converting forms of sentences. So these are inference rules as well. You guys know this notation. Alpha is logically equivalent to beta if and only if alpha entails beta and beta entails alpha. This is maybe something new that you know now. However, these are useful because you can use these rules that you see here for converting from one sentence format to another when you want to use a theorem proving. So all of these are powerful tools that you also want to have in your arsenal for the theorem prover. Some concepts I want to talk about, which is validity and satisfiability. A sentence is valid if it is true in all models. So in other words, it's a tautology. So for example, the special symbol true is a tautology or valid. A or not A is a tautology. A implies A is a tautology. A and A implies B, which implies B. This is a tautology, right? So a tautology is whatever configuration you give to the variables involved, it has to be, the entire sentence evaluates to true. A sentence is satisfiable if there is some model and some configuration of the variables that make this sentence true. So for example, A or B is satisfiable. Why? Because you can either set A to true or B to true. Determining satisfiability of a sentence, meaning if I give you a general sentence, right, a general propositional sentence, right, in order for you to determine satisfiability, this is known as the SAT problem. It is not an easy problem to solve for the general case. A sentence is unsatisfiable if it is false in all possible models. So for example, this sentence here, A and not A, you cannot make this sentence true, right? Any setting of A, set A to true, the entire sentence becomes false. If you set A to false, the entire sentence becomes false, right? Determining unsatisfiability of a sentence is known as the unsat problem. This is co-MP complete. So why am I mentioning validity, satisfiability, and unsatisfiability? Well, validity and satisfiability can be used to establish KB entails alpha. How? Validity is connected to inference via the deduction theorem. The deduction theorem says that KB entails alpha if and only if KB implies alpha is a tautology. That is, we show that KB implies alpha is true in all models. You can actually do this with model checking, right? So the validity way or the deduction theorem is what we've seen so far. If you do model checking and you check that KB implies alpha is true in all the rows, this would be checking validity. What about satisfiability? Satisfiability is connected to entailment via the following. KB entails alpha if and only if KB and not alpha is unsatisfiable. So that means we can show or answer the question of KB entails alpha if we find that KB and not alpha is unsatisfiable. That is, we show that there is no model for which KB is true and alpha is false. This is called proof by contradiction or refutation. We assume that alpha is false, which leads to a contradiction with a KB. Okay, so we'll show two ways. One is a direct proof, and another way, which is a proof by contradiction. Before that, I want to talk about inference rules. Inference rules allow us to take a sentence as input and then output it allows us to take a set of sentences as input and then output a single sentence. They can be depicted in two ways. This is one way to depict them. So this is sentence 1, 2, all the way up to n. And this is the conclusion sentence, or you can write them in this notation as well. The sentences before the line are called the premises. They are used to draw the conclusion sentence. Semantically, what it means is the following. What you're saying is, if all the premise sentences are true, according to your knowledge base, then the conclusion sentence here can be taken to be as true. This tells us that if in our knowledge base we have a matching premises, then we can add the conclusion to the KB as a fact. So using this notation and these inference rules, what are some known inference rules we can use? Here are our popular inference rules that are helpful. First one is modus ponens. If you have two sentences and they look as follows, alpha implies beta and alpha, then you can conclude that beta has to be true. And this makes sense, right? If alpha is true and alpha implies beta is also true, then it must be the case that beta is true. Another one is and elimination, called the simplification rule. If alpha and beta is true, then this implies that alpha is true. And it also implies that beta is also true, right? Because this can't be true unless both these sentences are true. Modus tollens. If not beta is true and alpha implies beta is true, then this you can conclude that not alpha is true. All logical equivalencies that we've seen here, which is this table here, right? All of these conversions are logical inference rules that can be used in both directions. Right? So, for example, this alpha, the biconditional for alpha biconditional with B can be written as this, right? And you can also use it in the other direction. However, you cannot use general inference rules in both directions. So you can't say that if beta is true, then that means that alpha implies beta is true and that alpha is true, right? This is only a special case for the logical equivalence formulas, which is in the table. And you can see the table of inference rules at this following link. What I want to say is you are not required to memorize these inference rules. If there are questions in the exams, which of course there will be, you'll be given a cheat sheet that contains all the inference rules that you need, and you will use these inference rules in order to answer questions. Another very powerful rule, which is the unit resolution rule. If you have a sentence where it is a disjunction of literals, right? And by literal, a literal in propositional logic, right? It consists of a symbol like P, and this symbol may be what we call is a positive literal, like P here is a positive literal because it doesn't contain a negation. But if we said not P, this would be a negative literal. So the literals that you see here, L1 to LK, they are either a symbol or a negation of a symbol. So in the unit resolution rule, if you have a sentence that is a disjunction of literals and another sentence M, where there is some Li here that is a complement of M. So in other words, you may have Li here equals P and M here is not P. If this is a case, then what happens is you can then conclude this following sentence. What you notice is you have L1 to Li minus 1, and then Li here is removed. And then you have Li plus 1 all the way up to Lk. So in other words, these two literals cancel each other out from the disjunction. Okay? So if you have two literals, Li and M, and they're complementary, you can conclude a disjunction of literals where you cancel those literals out. There's also the full resolution rule. You can have two, disjunctive sentences, right? And if you have Li and Mj are the complementary literals, then you can just union those two sentences. But very important, you need to remove the Li and the Mj, right, from the conclusion disjunctive formula. Here's an example. Here's our two sentences, A or B or C, and A or not B or D. Okay, if we use the full resolution rule on this sentence, you can see what are the complementing literals. It is B and not B. So when we union them, we get A or C or D, right? We removed the B. So this will be a useful rule for one algorithm we will discuss, inshallah. One important thing about the resolution rule, you are only allowed to resolve one literal at a time. So for example, if you had this sentence here, A or B or C or D, and not A or not B or not C, you can see that we have these two complements. We have B and not B, we have A and not A, right? So these are three possible complements. When you resolve, you're not allowed to resolve more than one literal in one go, right? What you're allowed to do is pick one literal, right? So for example, here I said A or not A, I added it, and B or not B. So you can see that I removed the C and not C. When I do this, I union both sentences that are remaining. I get A or not A, B or not B, or D. What you notice is that this A or not A evaluates to true, and anything ORed with a true will evaluate to true. So I hope this is clear. When you resolve, you are only allowed to resolve one literal pair at a time. So let us try to construct a direct proof for the same example we gave with the Wampus world. If you remember, this is the sentences in our knowledge base. We want to use a direct proof, right, to show that KB entails not alpha, and we will use the inference rules. So using the KB facts and inference rules, we can proceed as follows. What we want to do is, when you proceed with inference rules, you start with your knowledge base, and you want to start with sentences that contain your the symbols in your query. So when we look at the sentences here, it looks to me that this is definitely a relevant starting point here, right? So I'll generate a new sentence. I'll call it R6, and I'm going to do biconditional elimination of R2. This is one inference rule I could apply, right? So I break this into two implications. From this, I can also use simplification. If you remember alpha and beta, I can infer both that alpha is true and beta is true, right? So from and elimination, I can infer that this sentence is true. And then from here, I can also use logical equivalence, the contrapositive. I use the contrapositive here to flip the implication. And then here I used modus ponens with R8 and R4, right? So I took R8 and I took R4 and I used this modus ponens rules in order for me to infer this sentence here, not P1 or P2. Then here I say not, I use De Morgan's with R9. Then finally, I can use and elimination with R10, right? So you can expect questions like this in the exam. You are given a knowledge base in propositional logic, and you are asked to use a direct proof to prove a query. And you are going to be given a cheat sheet with inference rules. And the notation in which you answer the question should follow something like this. You add new sentences and you explain to me which rules you used, right? But this is how you would use a direct proof. So from the previous example, what we just seen, this is a direct proof inference algorithm. We can apply the inference rules to the sentence in the KB until alpha is added. This is known as a direct proof. During this incremental process, the KB is increased with more sentences. We can use a search algorithm for this, right? The application of the inference rules is similar to actions, right? So we can implement this as a search algorithm, BFS, DFS, to search these proofs by modeling it as a search problem. The initial state is the initial knowledge base. An action is the set of actions that consist of all inference rules applied to all sentences that match the top half of the inference rule. The result of an action is to add the sentence in the bottom half of the inference rule to your knowledge base. The goal is a state that contains the sentence we are trying to prove, right? So our state, if you remember, it is the current situation of the knowledge base. If our knowledge base contains the query we are trying to prove, then we are done, right? So I can do a search algorithm direct proof implementation. This type of direct proof can be more efficient in practice than model checking or this truth table enumeration, because we might be able to get to the goal without involving a large number of symbols. However, in general, the worst case can still be exponential. Why? Because as you recall from the search algorithms, all the search algorithms in general have exponential time complexity. Using search algorithms with inference rule, meaning this direct proof search process, it is a sound inference algorithm. The question is it complete? The reason it's sound, by the way, the reason it's a sound inference algorithm, because we use inference rule and inference rules are sound. However, is it complete? Well, it's complete with this following caveat. If the inference rules are sufficient to get to the goal and we use a complete search algorithm, then yes, this would be a complete and sound inference algorithm. What do we mean if the inference rules are sufficient to get to the goal? Well, imagine if we uh, look at the inference rules that we have in our cheat sheet and we removed one of those inference rules. If we removed one of those inference rules, that inference rule may be crucial in order to construct a direct proof. So this is what we mean. The inference rules need to be all there and provided for the search algorithm for it to be complete.